Okay, good afternoon. Continuing where, no, not continuing where we left off. Administrative announcement, tomorrow's dim sum. Meet at 10:30 outside the Berkeley BART station, or meet at 11 at Legendary Palace. If you Google Legendary Palace Oakland, the first hit has the address and everything. I put back up this chart of the 3 layers of abstraction about concurrency control. The wording's a little different from what I said last time. I'm abstracting away from my abstraction, my representation of the abstract version. So up at the top, it now says protect a control abstraction. So that's what chapter 1 was about, remember, is control abstractions. The most basic control abstraction is a procedure, and that's what we're protecting with the serializers in Scheme in this course. But objects are another kind of control abstraction, or there could be other things in different programming paradigms. But in any event, what you would like a user to see about this is the ability to control concurrency with respect to whatever form of control abstraction is in use, rather than with respect to lower level things like machine language code. And the middle level has the idea of a critical section, where we are talking about machine language code. And then the bottommost level is that there has to be some way to read and write the value of a memory location atomically, meaning that nothing else can break in between the reading and the writing. So, and then right at the end of last time, I put up the 4 different things that can go wrong, and that's what I want to go through in more detail today. So incorrect results. The key thing for you to remember is what the definition is of correct and incorrect results. Because in the kind of programming we're talking about here, there isn't just one possible correct answer. There might be more than one correct answer. But a correct answer is one that is consistent with some sequential order of evaluation of the different threads. Okay? So that's not saying that you have to do the threads sequentially. It's saying you have to get the same answer you would have gotten if there weren't any parallelism at all, if one of them entirely happened before the other one started. So it's entirely possible that if A happens before B, you get a different answer from the one you get if B happens before A. That's okay. Both of those are correct answers. But what's not correct is something that's neither of those. Okay. So in order to be assured of getting correct results, we have to put in concurrency control, which is to say we have to put in some kind of restriction on when things can happen in parallel. But if we go overboard with this, if we put in too much restriction, then instead of incorrect results, we're going to get inefficiency, where one of the threads is sitting there idling, twiddling its thumbs, when it really could be working in parallel with the other thing, and it would be okay. Yeah? Okay, so the question is a result correct if it's the same result you would have gotten sequentially, but you got it through an incorrect process? The definition of a correct process is one that's guaranteed to give you the same result as you would have gotten sequentially. It's up to the implementation how to achieve that and still get you as much parallelism as it can. So it's kind of hard, it's something you have to learn through practice, to get the right granularity of concurrency control. If we just say anything that has reference to anything in memory can't be in parallel with anything that has reference to anything else in memory, then you've done away with the parallel capabilities of your system. It's as if you had one processor instead of a bunch of processors. On the other hand, if the control is too fine-grained, then you might be able to get incorrect results. So an example I like to think about is the one about airline reservations, because very often you have to take two flights. There isn't any direct flight from point A to point B, and so you have to go by way of Chicago, right? It's always Chicago, unless it's LA, which is even worse. And so you're requesting two different seats on two different flights. And the question is, how should we put in concurrency control for this? So an example of something that would be too coarse of a parallelism is we'll only accept one request at a time for a given flight date. Okay? Obviously, if I'm trying to get from here to Boston and somebody else is trying to get from Timbuktu to Kalamazoo, there's no reason why we have to get in each other's way. I mean, we're going to be looking at entirely different flights. And a lot of people want to fly on the same day, especially if the day is tomorrow. So it would be really bad to have the parallelism dependent just on the flight date. So then maybe it's the flight number on a given flight date. So I'm going to be on flight 724 from here to Chicago on such and such a date. And nobody else is allowed to do seat selection or actually to make a reservation even, because they might run out, for that flight on that date in parallel with me. Well, that's possibly too fine-grained and possibly too coarse-grained. So, for example, let's suppose two people are requesting the same flight on the same date, but one of them likes window seats and one of them likes aisle seats. And so we make different seat requests. Could those be handled in parallel? Yeah. But if we use flight number and date as the criterion for parallelism, then they won't be done in parallel. On the other hand, since I'm going to be on two different flights, another situation that we'd like to avoid is for me to get a reservation from here to Chicago, but not get a reservation from Chicago to Boston. Okay, that would be pretty bad. I would be stuck in Chicago. What could be worse? And so we really want to restrict parallel access to both flights at the same time. Okay, that's the sort of thing that might make us actually want to say, well, only one person on a given flight date, because of this need to have two different flight numbers and control access to both of them simultaneously. But the solution that's used for that problem, instead of trying to restrict against everything that happens on that date, is to say, I want two serializers or two mutexes at once. One of them for my first flight and one of them for my second flight. And I shouldn't be able to make my reservation unless I got permission to use both of those protected serializers at the same time. Okay? Well, that's a little tricky. Because once you're asking for two serializers at once, you run the risk of the third problem, which is deadlock. Actually, there's a simple solution to deadlock for the case of flights. So let me talk instead about the example that's in the book, which is suppose I want to transfer money from account A to account B as a single transaction. So I need to control access to the from account and the to account at the same time. Okay? So how am I going to write that code? So let's say that every account has a serializer associated with it. So I'm going to say something like serializer, called from account serializer of to account serializer of transfer, which is a procedure. And I'm going to call that with from account and to account as its arguments. Okay? So everything from this parenthesis to this one is getting me a version of the transfer money procedure that's protected with respect to both accounts. So any questions about what this is doing before we go on to what's wrong with it? Okay, no questions because you don't understand, or no questions because you do understand. So got it, sort of, don't got it. Okay, some of each. Let me try again. Suppose we weren't thinking about parallelism at all. And I asked you to write a procedure to transfer money from one account to another. I want to transfer $100 from your account to my account, let's say. You would write a procedure called transfer that would take two arguments, the from account and the to account. And I'm being vague intentionally about what an account is. Maybe it would be the account number, or maybe it would be some object that represents the balance of the account and the account number, and the serializer would all be in there, and so on. So I don't care about that, but you're going to write transfer from account in some form to account in some form. Okay? Everybody clear on that? What the problem is we're solving? Good. Okay. Now I want to worry about doing this in parallel with other people doing transactions on different accounts. And we looked last time at how things can go wrong if two people are using the same account at the same time. If I'm trying to deposit money and you're trying to deposit money to the same bank account at the same time, one of our deposits might not actually happen unless we make sure that those two transactions are serialized. Serial meaning one after the other, not the stuff you eat for breakfast, but more like a radio or TV serial where there's an episode and another episode and another episode, one after the other. If there was just a single account involved, we would say my account serializer of transfer, and that procedure call, calling the serializer with the transfer procedure as argument, gives us a protected transfer procedure. Right? Remember that from last time? So you call the serializer, it takes a procedure as argument, and it returns the same procedure, only protected now with respect to other people using the same serializer. Okay, unfortunately for transferring, if we just want to deposit or withdraw money, that's fine. If we want to transfer money from one account to another, there's not just one account involved, there's two accounts. And we have to make sure that nobody is simultaneously changing the balance of either of those accounts. Okay, who's still with me? Great. Okay, so one way we could do that is to just have a very broad kind of serialization where nobody's allowed to do 2 transactions on any accounts from our bank at the same time. But that would mean that all the ATMs in this bank's network minus 1 would be unusable at any given moment. So we don't want that. We want it to have a specific protection for this bank account, except now there are 2 bank accounts. So what I did is I called, in here, I called 2 account serializer on the transfer function. That gives me a version of the transfer function that's protected with respect to other people using the 2 account, the one we're putting money into. Okay? So we're safe as far as 2 account is concerned, but we're not safe about from account yet. So I take the protected procedure that I got from this serializer and use it as the argument to this serializer. So now I have a transfer procedure that's protected against the 2 account and is also protected against the from account. Okay? So this procedure that I've gotten from these parentheses marked with a tick mark here, what that gives me is a version of the transfer procedure that's protected against both accounts simultaneously. So if I win, if I get both of these serializers, while the transfer procedure is running, nobody else can use from account and nobody else can use 2 account. Yeah? Does the order of the serializers matter? That's a great question, only I'm not sure quite what question you're asking. It's going to matter a lot in a second when I talk about deadlock. But as far as the protection aspect is concerned, no. If we succeed in getting both serializers, then it doesn't matter which order we got them in. Okay? The important thing is that we have both of them before we do anything substantive. Okay? Other questions? Okay, great. So now you have the idea of protecting 2 things at once. So you see how that would work in the airline case. It would be serializer for my flight from here to Chicago of serializer of my flight from Chicago to Boston of seat reservation, right? Got that? So if I need to make a reservation on 2 flights and it's no good to me to have one without the other, I have to get both of them or neither of them, then we have to use both serializers in order to be properly protected. Okay? Now, here's the problem with this. What happens if thread A is trying to transfer money from you to me, and meanwhile, it just so happens that thread B is trying to transfer money from me to you? Okay? So you get the picture? You and I are having battling ATM wars, trying to transfer money to each other's, and we want to make sure that the result of this is consistent with them happening sequentially, which is first we transfer money this way, then we transfer money that way, or the other way around. And in either case, we transfer the difference between the 2 amounts from the bigger amount guy to the smaller amount guy. Okay? Well, what happens? So if you think about serializers being implemented in terms of mutexes, which control a critical section, so something that we say, acquire the mutex, run the code, release the mutex. All right? This, when I call this procedure, which mutex are we going to acquire first, from account or to account? To account, everybody says. And I think you're wrong. I think what's going to happen is this. When we make a serializer, it says, construct a piece of code that says, get my underlying mutex, and then do whatever I'm protecting, and then release my mutex. Now, in this case, whatever I'm protecting is this inner procedure. So when we have both of these serializers on top of each other, it's going to be acquire from, acquire to, transfer, release to, release from. Okay? That's the sequence of events within a thread. Okay, now let's look at the sequence of events looking at both threads at once. This guy says acquire the from account, which is you. Okay? I'm being very hand-wavy about the notation because the notation doesn't matter. What matters is the idea here. So I say acquire you. Now, it just so happens that at that moment, this thread gets to run. It says acquire the from account, which is me. This succeeds, and now we're in trouble. Because this guy is going to try to say acquire me, which will fail because he's got it. And this guy is going to try to say acquire you, which will fail because he's got it. Okay? So these two threads need two different concurrency controls, and they acquire them in the other order because from each other because one is trying to transfer money from me to you, the other is trying to transfer money from you to me. And if we're unlucky, one of them gets one, the other one gets the other, and then they're both stuck. That's why in some of the earlier literature, deadlock is called deadly embrace. You can see what's going on. These two threads are each one waiting for the other one to finish. Okay? Questions about what the problem is here? Who's getting it? Great. Okay. That's a deadlock. Now, how can we solve this problem? There are various ways. Sometimes there's a natural ordering, and if the different procedures use the natural ordering consistently, everything will be okay. So in the case of the airline with the two different flights, I have to take the flight from San Francisco to Chicago before I take the flight from Chicago to Boston, right? It doesn't make any sense to do them in the other order. So if the software for making a two-flight reservation always first asks for the first flight and second asks for the second flight, then if two people are trying to make reservations on that pair of flights, they're both going to ask for the same flight first. At most, one of them will succeed. And the one that succeeds can then ask for the second flight, and that'll work too. Okay, there isn't going to be a deadlock in that case if everybody starts with the chronologically first flight. Okay? Well, that doesn't work for bank accounts. For bank accounts, however, we can impose an ordering arbitrarily. And the way we do that is you have a bank account number, and I have a bank account number. So instead of saying, get the from account serializer and then get the to account serializer, we're going to say, serializer for whichever bank account number is smaller, and then serializer for whichever bank account number is bigger, and then do the transfer. Okay? So that makes the code a little bit more complicated. You have to find out which one is bigger, and if this, do this, and if that, do that. But it means you don't have a deadlock. Some cases are way more complicated than this. If you study databases, CS186, you will find situations where you need half a dozen serializers at once. And what's more, sometimes you don't know you need one of them until you've already done some computation with the other ones. Okay? So if you know all the ones you need ahead of time, then it's easy to find a way to order them. Or at least it's possible to find a way to order them. But if you ask for, serializer X and serializer Y, and only then do you find out that you also need serializer W, okay, it's too late to ask for them in alphabetical order. Yeah? Do serializers not follow applicative order? No, they do. Yeah, okay, this is really tricky. I'm glad you asked the question because I'm sure there's 100 other people in the room who don't get it, and we're too timid to ask. He's looking at this code here, and he's saying, because Scheme uses applicative order, don't we call to-account serializer first? And therefore, shouldn't we acquire this mutex first? And the answer is yes to the first, no to the second, even though it sounds like they're the same question. Because everything in between these tick-marked parentheses happens before we actually try to do the transfer. Okay? And because of that, we haven't actually acquired any resources during this whole computation. All that we've done is construct a procedure which, when invoked, will acquire both of these resources. Okay? Only when we call this procedure with these arguments do we start thinking about which mutex do we need first. And the answer is to-account serializer, when we called it, generated this piece of code. Okay? From-account serializer now says, okay, let me protect this with respect to the from account by sticking acquire from at the top and release from at the bottom. We haven't executed any of this code yet. When we call this function with these arguments, we come into the top of this code and do things in this order. Okay, so yeah, it's really tricky, but this really is the right order. In any event, it doesn't matter. I mean, I'd like you to understand this, but as long as you understand that there is an order, and if another thread tries to do these in the opposite order, you're going to get in trouble. That's the important thing about deadlock. Okay? So some deadlock problems are very, very simple, and we can solve them by finding or imposing an ordering on the different resources. So you ask for a resource. If you need resources number 3 and 10 and 5, you ask for them in the order 3, 5, 10. Okay? And then everything works, because if you get 3, somebody else who needs the same combination isn't going to get 3, and so you can go ahead and get 5 and 10 without that kind of interference. Sometimes it's more complicated for various reasons, and so you can't solve the problem in that simple way. So how do you do it? Well, when you study operating systems, one of the things you will learn about is some very, very complicated, hairy, annoying, convoluted algorithms for trying to do analysis of the resource needs of different threads ahead of time to try to make sure that deadlocks can't happen. That's not what anybody does in practice. This is a trick that we all learned from the database people who invented it first. What you do is this. You go ahead and write the code in the easiest possible way, and you let deadlocks happen. Footnote. Remember that a single concurrency hit, where two processes need the same resource at the same time, is very, very rare, because your critical sections are short. They take maybe a microsecond to run. So we're talking about two people in the same microsecond needing the same resource. So it's very uncommon in the first place. In order for a deadlock to happen, you need two of those coincidences. right? So the probability of deadlock in a particular situation is vanishingly small. Nevertheless, since computers do things very fast, and they do things over and over again, sooner or later you're going to get a deadlock. So we can't just say, let deadlocks happen, I wash my hands of it. Right? People used to say that once upon a time, but it doesn't work. Instead, what you do is you start up another thread in parallel with everything else that you're doing, whose sole job is to poke around the operating system looking for evidences of a deadlock. So you look for, oh, this procedure is waiting for this resource, that procedure is waiting for that resource, but wait a minute, this procedure has that resource. So you find out that a deadlock is happening from the thread maintenance databases in your operating system. And then what you do is you just kill one of the processes. Say, sorry, you have to start over. So let's say we have A and B stuck in this deadlock over here, and the deadlock preventer notices this, that they're both waiting for each other, and just kills A. So that causes A to release your account, and therefore B can finally succeed at acquiring your account. And then A has to start all over again, asking for your account and then my account. But now process B has finished, so we're not going to have that same problem again. In order for this to work, you have to be able to back out of a computation. So when I said kill the process, it's not that simple. You have to notify that process that it is in a deadlock. Not that thread, because it's stuck, but some other piece of that process, which has to figure out if it's in the... So why did we need concurrency control in the first place? Because we're changing the values of things, and there might be an inconsistent state in the middle when we've partly changed something and not changed the other parts. Okay? So what we have to do at this point is undo any changes to the database that process A has made and release its resources, and then notify it that it has to start again from this call. By the way, another solution that doesn't solve the problem of finding out halfway through that you need a resource, but does solve the other problems, and this is something else that's done in practice, is instead of having a system call saying, I want to acquire this mutex, you give it as argument a list of mutices, and you say, I want to acquire this mutex and that mutex and that mutex and the other mutex all at once. And you leave it up to the operating system to worry about deadlocks and reordering of the requests. If the requests all come in as a block, then you can do that. You can do the analysis of making sure that I can simultaneously acquire all of these resources. Sorry. Folks, this is just scratching the surface of how to handle deadlocks and how to handle concurrency altogether. You are going to learn this again more than once. So our hope is that when you get it the second time around with a lot more detail than you're seeing this week, you will say, oh yeah, I remember the big idea of this from 61A, so I can now concentrate on the details of how to make it work without having to learn what problem am I trying to solve. Okay, that's our hope here. Okay, resource starvation, the last thing on the list. I talked about this a little bit right at the end of last time. It's the situation in which several threads want a resource, and somebody wants it over and over again. And if that somebody gets it over and over again, so at any given moment there might be a bunch of threads all waiting for the same resource. And if the same one always wins, then those other threads are never ever going to get to run, and that's called resource starvation. it's okay if they're not 100% fair. If you know, thread A wins more than half the time, you know, that might seem unfair if there were human beings involved, but it's okay from a computer standpoint. As long as thread B gets to win eventually, then it's okay. But in certain situations, if you do your scheduling badly, it might be that somebody way down the list never gets the resource that it needs. So one simple thing that people do to prevent this is when the operating system is looking for who should get this resource, instead of saying, let me start with process 1 and see if it needs it, then 2, then 3, and work down in sort of process number order, you remember the process number that got it last time, start with the one after that, and work, you know, rotate back around, so that the same process doesn't get it twice in a row, and everybody gets a turn. Sort of round. That's called round-robin scheduling. Okay. So once again, I'd like you to remember what the 4 things are that can go wrong, and have some sense of what they mean. After the final exam, I don't expect you to remember any details about how we do serializers in Scheme and SICP. Okay, that doesn't matter. What matters is what is the problem we're trying to solve? What mechanisms do we have to solve it at different levels of abstraction? It's like, what's a critical section? You're going to hear that term again in other courses. What can go wrong? How can we solve the problem? And that's really it. So what counts as correct and incorrect results? Under what circumstances do and don't you have a deadlock? Have some understanding about the question of granularity of protection. So fine-grained protection might give you incorrect results. Coarse-grained protection might give you inefficiency. I'm trying to steer your way through that, in simple cases at least. And finally, just in the back of your mind, when you're scheduling an operating system's allocation of resources, make sure you don't starve some process down at the end of the list. Okay. So now I want to talk about why we need these levels of abstraction. In fact, why do we need any kind of support at all for serialization other than just plain old scheme code, like that up on the screen? So this is an attempted implementation of Make Serializer that doesn't work. So first, let's look at how it's supposed to work, and then we'll see why it doesn't. So Make Serializer is the sort of the serializer class, right? It's the procedure that makes an instance of a serializer. The instance of the serializer that it's making is created by this lambda right here, which is inside a let. And so in use question mark is an instance variable, a persistent state variable for each instance of serializer. In other words, every serializer has its own in-use variable, which starts out false. Initially, the resource is not in use. So the serializer is this lambda where the cursor is blinking. And what does it do? It defines, it defines something called protected proc. And that definition comes down to here. And then finally, in this last line, I don't know why this is doing this. Here we go. Finally, in this last line, we return protected proc. So the value returned by Make Serializer is not, the value returned by a serializer is not the result of calling a procedure. We're not actually going to do anything to the underlying data. It's just a protected version of proc, which was our argument. And we're going to return that. So what does protected proc do? Well, it's written to take any number of arguments. So that's why it's protected proc dot args. So args is a list of all the arguments. So the first thing we do is look to see if this serializer is already in use. If it is already in use, then we have to wait a while. This is, of course, very hand-wavy, because I don't care about this aspect of it. It means let the operating system know that my thread is yielding up control and somebody else can run for a while. And then when it's our turn again, we call protected proc, again, this procedure, protected proc, with the same arguments. So we keep doing that. Basically, this is a loop calling protected proc over and over again until finally in use is false. If in use is false, then we start doing this stuff. We set it to true so that nobody else can get in. Then we call the underlying procedure proc with the arguments. We have to use apply here because args is a list of the arguments to proc. So you can't just say proc args. You have to say proc arg1, arg2, arg3, etc. And the way you do that is you use apply, which does take a list of argument values, as you know. So we do that. Call the result. Then, since we've called the procedure, we can now set in use to false and return the result. Okay? What's wrong with this code? Yeah. How could it have an incorrect result? Yeah. Okay. So I would explain the problem a little differently. He's saying, what if two procedures get to this point at the same time? Well, that isn't supposed to happen because up here, up here, we check to make sure that in use was false. So if in use is already true, we shouldn't be doing the setback. And they're right after each other. As soon as we see that in use is false, we come right down here, and the very first thing we do is set it to true. But that's not good enough. Because somebody could sneak in, some other thread could sneak in between reading in use and writing in use. Okay? It's kind of hard to wrap your mind around this way of thinking where, two consecutive instructions, that's not close enough to prevent problems. It has to be one atomic operation. So we're going to have some kind of supporting mechanism to let us read the value of in use and set the value of in use simultaneously. The book provides a simulated computer instruction. You're supposed to imagine that it's a machine instruction, even though it's a scheme procedure, called test and set bang, that takes a memory location and a new value. It puts the new value in the location, and it simultaneously reads the old value and returns it. So we could write this by up here. We would say test and set bang, and it turns out they don't use variables. They use the car of a pair, because a variable isn't exactly the same thing as a memory location for reasons that don't matter. So I'm going to, for this moment, just pretend it's a variable. So they're going to say test if, parenthesis, test and set bang in use, true. And what that procedure call is supposed to return is the old value of in use. And we can use that in the if. Now, if we lose, if somebody else is already using it, haven't we sort of cheated by setting the value to true? Well, yes, Technically, we weren't allowed to set the value of in use unless it was false. But there's only two possibilities. Either it's false or it's true. If it's false, then we can do what we want. We've won. We're in. If it's true, and we're setting it to true, we haven't done any harm. Okay? Whoops. I don't know what I clicked. So you might worry about, what if at the same moment I'm doing this test on setbang, the other thread that has this resource is freeing it? And yeah, I really have to worry about that too. But I'm not gonna for our purposes. It's enough for you to understand why it is that we have to be able to do both of these things at once. Now, I'm talking as if we're implementing serializers directly in terms of the hardware support. But that's not what the book does. What the book does is it implements serializers in terms of a mutex. A mutex, as seen in this chapter, is an object, something that takes messages and carries out methods. And its messages are acquire and release. So the acquire method tries to acquire the mutex. If it succeeds, just return. Returns whatever. It doesn't matter what its return value is. If it fails, it keeps trying. It sits there looping until it can succeed. So acquire says, sit here inside this resource until I'm able to acquire it. And then you do call the procedure, the apply proc args part. And then you say, you send your mutex the message release. And inside the mutex, there'll be an in-use variable that it sets to true or false. The advantage of having two levels of abstraction is that you can write your higher level code without knowing anything about exactly how your hardware provides atomicity support. You can leave that to the people who write the operating system. Okay? Because there are different ways. A test and set instruction is one way, but for reasons you'll learn about in 61C, it's undesirable to have two memory references in the same instruction, two data memory references in the same instruction. And so one architecture that I know about, the MIPS architecture in 61C, what they do is there are two different instructions. One that's called set this value protectedly, and the other that says, okay, clear the protection flag. And what it does is the hardware associates an extra bit, one on-off value, with each word of memory. And if you do this protected set, it checks that bit, that one bit, see if it's on or off. If it's off, go ahead and do the set and turn it on. And that's all done in the hardware. And if not, it just fails, and you have to come back and try again later. And clearing the bit just clears the bit. So this means you're only doing one memory reference. You're doing a set. But this hardware control only lets you do the set if that extra bit is 0. So that's a whole different way of making the hardware work. It's not exactly a test and set, because you're not reading what the old value was. You're just putting in a new value, I think. Oh, no, I'm sorry. I take it back. I'm wrong. It is reading that you're doing. So we do the protection directly on the variable x that we're interested in, not a different in-use variable. So we say, read the value of x and set the bit that says I'm using it. And then you do your computation, like adding 1 to it or whatever. And then you say protected set. And the protected set will fail if anybody else has tried to read that value meanwhile. So it's a way of having two different instructions that essentially work like a mutex. That it's like a hardware implementation of a mutex, where the hardware has this extra capability to ensure that you don't let another process read the value while you're doing your computation. And then when you write the value, that automatically releases the mutex. Okay? Don't worry about the details of that. You don't have to know it. All you have to know is that different kinds of hardware do this differently, and that giving us a level of abstraction in between what the hardware does and the higher order control structure that we're interested in pushes the problem from the programming language down to the operating system to worry about the particular kind of hardware that you're working on. So you can write a program that will work on any hardware. Okay, go. See you tomorrow if you come to dim sum, otherwise Monday.